The model that we're going to look at in this video is called break-even analysis. And to look at the break-even analysis problem, we're going to investigate an example problem that involves producing a new metal component. In our case, we have identified two options for creating this metal component. The first option is a manual operation where a skilled machinist simply machines the part. To do this, it takes 4 hours at $100 an hour, and so the $100 an hour is the machinist time plus the overhead associated with the equipment that the machinist is using. The second option is to cast the part, and prior to casting or prior to making the first part, we have to create the die in order to do the casting operation. And so creating the die takes 100 hours of a die maker's time at $125 an hour, again including overhead and equipment costs and so on, plus $10,000 in steel to create the die. Once the die is set up, the casting of each part requires 15 minutes to cast. Casting operators are at $40 an hour, and then finish machining to clean the part up takes 30 minutes at $100 an hour. So the question at hand is, which method is preferable? Would we rather do option 1 or would we rather do option 2? In order to make this decision, the first thing we have to decide is what's the basis for the decision. What are we going to use as the metric to select option 1 versus option 2? And so our metric is going to be cost. We want to compare the cost of option 1 with the cost of option 2 and make the decision on the basis of that cost. So in looking at the cost, the first thing we have to recognize is the cost of both options depends on the number we produce. In other words, for option 1, the cost depends on how many machined parts that I create. And so if we let Q be the number of machined parts, the cost is simply Q times 4 times 100, 4 hours at $100 an hour, or 400 Q. If we look at option 2, oops, that's an O. Let's see if I can redo that. Option 2, we have this initial cost to create the die, so we have 125 times 100 plus 10,000 plus now 1/4 of an hour times 40 plus 1/2 times 100 times Q. So we have 22,500 to create the die plus $10 for casting, $50 for follow-up machining, so 60 Q. And so option 1, 400 Q, option 2, 22,500 plus 60 Q. Okay, little mishap when I switch videos, but that's okay. We can get these back. So for option 1, as you recall, the cost per unit was 400 Q. And for option 2, the cost was 22,500 plus 60 Q. So we had those on the previous ones that I accidentally lost. And so what we want to do first is we want to look at those in a graph. So let me change my pen color here, change it to black, and create our graph. And what I want to plot is the cost versus Q. And so for option 1, it's simply 400 Q. So we have a nice linear relationship, and we can plot that as follows. And this is, oops, didn't mean to do that. Let's go this way instead. 400. And here we are at 0. For option 2, this is option 1. For option 2, we start here at 22,500. And we move up at a slightly different slope, or a significantly different slope, of 60. So we have a per unit cost of 400 Q for option 1. We have a per unit cost of 60 Q after we have this initial 22,500. And so what we want is we want to be able to look for any given Q, which option do I choose? And clearly I want to go back and change my pen color, ink color, make it red again. Clearly what I want to do is stay here along this bottom frontier. And so what we have at this point is Q star, or our break even, sometimes called the point of indifference. Since at this point it doesn't matter whether I choose option 1 or option 2. So this is option 2. At this point right here, the point of indifference, it doesn't matter whether I do option 1 or option 2 because they have the same cost. So if I'm to the left of my break-even point, clearly option 1 is preferable because I haven't made enough units to overcome this initial 22,500. Whereas if I'm to the right of my break-even point, then I have made enough parts to overcome my initial cost, and so I'd like to use the smaller per unit cost. And so the question is, how do I find the break-even point? So what we're going to do is we're just going to take our two costs, our two cost expressions, and set them equal to one another. 22,500 plus 60Q. And if we solve this, we're going to get 340Q. 340Q is equal to 22,500. Q is equal to 22,500 divided by 340, somewhere around 66.2 or something like that. So before we discuss this, let's generalize this a little bit. And if we look at our two options, option 1 and option 2, we can assume that we have a fixed cost plus a variable cost, or a per unit cost. And so in option 1, the fixed cost is simply 0 and the variable cost is 400. And for option 2, we have a fixed cost of 22,500 plus a variable cost of 60. And so if we expand our expression, we can say that our fixed cost for option 1 plus our variable cost for option 1 times Q is equal to our fixed cost for option 2 plus our variable cost for option 2 times Q. And if we rearrange a little bit, we can get Q is equal to variable cost option 1 minus variable cost for option 2 is equal to the fixed cost for 2 minus the fixed cost for 1. And so Q star is simply equal to fixed cost for option 2 minus fixed cost for option 1 divided by variable cost for option 1 minus variable cost for option 2. And you can see that's exactly what we have here. So this is the fixed cost for option 2. Option 1 didn't have a fixed cost, divided by the variable cost for option 1, which is 400, minus the variable cost for option 2. And so now we have this general relationship to determine what the break-even point. So let's discuss for a little bit what we did with this model. So what we were trying to do was select between two options. We had two options for making the part, and we were trying to select which method was preferable. And so the first thing we decided is that we would use cost as our criteria. So in other words, we wanted to select the option that had the smaller of the two costs. In order to do that, of course, we had to determine what the cost for each option was. And so the key for this particular problem is to recognize that the cost for the solution, either solution, depends on the number of parts that we make. And so for option 1, the cost is going to be 400 times however many we make, whereas for option 2, we have the fixed cost of 22,500 plus this variable cost. And so once we identify our two cost expressions, we as a side did a simple plot so that we could observe the problem that we're trying to solve, and then we solved for this point of indifference, or the break-even point, by simply setting the two expressions equal to one another. Since both were expressed in terms of Q, that's what we're really after. We're after this indifference point so that we can then make a decision. So we came up with the indifference point, and then our decision is based on what the actual Q is relative to Q star. So if you're given a particular Q, in this case 500 for example, we're going to be somewhere out here, and so our choice is option 2. If we have a Q of say 10, then and we're going to be somewhere here on the left side, and then our choice will be option 1. Then we expanded, or we generalized a little bit to use this notion of a fixed cost and a variable cost for both solutions, and we came up with the general expression for determining the break-even point for any two alternatives that involve this fixed cost and variable cost configuration. So the last thing we'll do in this module is we'll look at an Excel version of our general model. So let me grab, if I can get around to it, let's grab our Excel version. And you can see what I have here is my fixed and variable costs, so F1 and V1 and F2 and V2. And then we can, given those, we have our relationship here, which is for the break-even point. So fixed cost 2 minus fixed cost 1 divided by variable cost 1 minus variable cost 2. And you can see that's exactly what we have here in cell B5. We have fixed cost for 2 minus fixed cost for 1 divided by variable cost for 1 minus variable cost for 2. And you can see that gave us our break-even point. In this case, I just have the values set in from our previous problem, but since we've generalized the model, we can use any value. So if we do in fact have some fixed cost for option 1, and maybe we have a lower, I didn't want to do that. Let me change this one, a lower variable cost. And if we could somehow reduce our fixed cost here, 20,000, and then maybe this goes up to 61 or something like that. You can manipulate the numbers however you like, and then what the model, the Excel model, gives us is two things. It gives us this break-even point and gives us this graphical analysis that we can use to ultimately make the decision. Because remember, the goal here of the model is to provide us information. The model doesn't give us the exact solution. It doesn't tell us exactly what to do. The model provides information for us to make in order for us to make the ultimate decision.